All right, we're going to get started. Hi, and welcome everybody. I'm Tom Talpey from Microsoft and my colleague Mathew George. We are here to talk about an experiment that was performed in the recent past with SMB3 push mode, which is low latency RDMA to persistent memory using the SMB3 protocol. And so the outline of our little chat here is that I'm just going to give 5-10 minutes of background on push mode, what it is and how to make it work in some prototypical way. Not the final way, not the best way, but just a way that allows us to evaluate how well it works, how quick it is, how fast it is, what its latency and its overheads are. Mathew is then going to dive into the actual prototyping and the actual results that we had from this effort. And I guess we should say this for the benefit of our colleague Ned Pyle. This is not a commitment to ship it in Windows. Hopefully you'll see it someday, but we're not talking about a product feature yet. We're talking about an experiment that we performed using the Windows operating system and some familiar NICs, but it is not yet a feature that you can drop on your foot. So, background. Here's a picture you may have seen before called push mode, and it shows SMB3 using RDMA in push mode. Push mode effectively enables zero-copy remote read and write, primarily write, but read and write, to a DAX, direct access file, that is a file that resides in a PMEM, in a persistent memory device that's been mapped as a file system in Windows. This is all standard stuff. Windows has supported RDMA since 2012 and has supported DAX since 2016, all right? So you can build this system apart from the protocol plumbing today. You could have built it, 3 or 4 years ago. There are multiple implementation options, however, for SMB3 push mode, and this is what's been talked about in the past. The first option is traditional I/O, regular old SMB3 reads and writes that happen to land in a DAX file, okay? It uses the I/O stack, this skinny line called I/O requests, right? That's the way we do it to a disk or a solid-state device. It's basically a bunch of ERPs in Windows that flow down. The more interesting way is to access the DAX mapped file directly, and there are two ways that we envision doing this. The first is one that we talked about, I think, 1 year ago, maybe 2 years ago, an intern experiment that we did within Microsoft in the SMB team that basically does copies, not I/O requests, but copies from the SMB3 process into the DAX file. And we got some numbers from that, and they were okay. They were better because DAX is more efficient than an I/O stack and a disk, but they weren't groundbreaking. And so our goal was to push it forward to this so-called phase 3, where we actually do direct RDMA using SMB to set up and manage the connection to the DAX file, right? So we completely offload all the data management to the RDMA device. We bypass the CPU altogether, except for setup. Here's a quick diagram of it. You can see the black lines at the top are the setup. The client, who's connected to the server, negotiated the protocol, created a session, all that other stuff, will then open a file. And it will basically perform a create and subsequently send a magic FS control that requests that the server register the memory of the DAX file and return the memory region handle to the client. This is a one-time setup operation that allows the client to perform RDMA to the server. That's the opposite direction from what we normally do in SMB. We're going to push. That's what we call this push mode. Normally in a write, we send the server a request, the server performs a read, and then writes the data. Here, the server doesn't even know we're doing a write. He gave us a handle, we're just going to jam data down to that file. So you can expect that you're going to have much lower latency and zero overhead on the server. The server CPU literally does nothing here. So that's pretty cool. And then at the end, there's some teardown and stuff. And I guess I just want to mention that you can read as well as write. That purple line in the very middle is this new flush operation, and that's what we're going to have to play with to do our prototype. So the flush operation is an RDMA protocol extension. It's being discussed in the RDMA community. I talked about it a moment ago in our SNIA NVM programming twig session that happened just next door half an hour ago. It provides a remote guarantee of durability. It's basically a flush like a local flush would be, but it operates in the RDMA adapter. And there's a bunch of behaviors of it on what bytes get flushed and what the selectivity and scope of the flush are. But it is still emerging. It has been talked about for a long time. There's strong consensus in the RDMA community. But it has yet to become a full-blown standard. There's an additional standard that we see related here in the PCI bus to allow flush from the adapter all the way to memory. There are ways to do this on a platform-specific basis. We'd like to have this portable, universal way over the PCI bus. In any event, none of this is quite here yet. We don't have a flush operation yet. The protocols haven't been extended. The implementations within the platform haven't been finalized. We can do it, kind of, and this is how we're going to experiment. So what we do is we go into our Wayback Machine to SDC 2016. I'm pretty sure it was 2016. I should check this. Where Chet Douglas, an Intel employee, talked about platform workarounds to implement flush via an RDMA adapter. And his first slide was basically to describe the Intel architecture and these three things: ADR, the asynchronous data refresh, DRAM refresh, IIO, the integrated I/O controller, and at the bottom, DDIO, data direct I/O. And this is this fairly interesting feature that's implemented in the Perley platform first. I think DDIO might precede it, but this ADR is a Perley feature that allows our DMA devices to go to the CPU cache, to the LLC, the last level cache of the CPU, via this feature called DDIO. This thing is evil with respect to persistent memory because it steals the memory from the memory controller and puts it in the CPU cache. And in order to flush it, you have to send a message to the CPU saying, would you please flush your cache? The I/O device cannot cause the CPU's flush to cache. So this is a real pain, and how do you implement flush? Well, he had a number of workarounds, but the interesting one is turn off DDIO, right? Make the data go to the memory controller just like it always did. And basically, there's a few flags, but if you notice in that first slide, you had a bunch of arrows that went from left to right here in the picture, right? From the PCI root, oops, all the way to the DDIO. Here, I'm hitting the wrong button. I'm going the wrong way, so sorry. Here we see no lines on the right. Okay, so it goes straight to the IMC, the integrated memory controller. Once it's in the IMC, we're inside that dotted line called the ADR domain. And once we're there, we're home free. That's persistence. That little dotted line is the persistence boundary. So that would be cool. How do we do that? Chet actually told us how to do that back in 2016. There are some magic bits in a PCI configuration register at offset 0x180 in this PCI root device. And there are only 2 bits you have to change. They're bit 7 and bit 3 in 1 byte of that PCI configuration register. And gosh darn if they don't do what we want. One of them turns off the bit that says use allocating flow. And allocating flow means allocate a cache line for this write. So we turn that off. And then second, we command the PCI devices to do the same. And so, poof, we turn off these 2 bits and we have a device, an RDMA adapter, which can write directly to persistent memory. So flush becomes simply a matter of getting the writes out of the device and into the motherboard. By the way, there are 2 bits there, and you can see at the very bottom it says they read 99 by default. Intel doesn't tell us what those 1 bits are. You know, it should be 88 based on this because they don't define any other bits. But magically, 2 other bits are on. So we only clear the 2 bits, and we leave the other 2 bits on, and magically it all works. So when we do this, our workaround becomes a simple matter of replacing an RDMA flush with an RDMA read. The behavior is effectively identical. We don't want to standardize this. This is an incredible hack workaround that'll only work on a system that you've also hacked physically by changing a bunch of PCI configuration registers. At great risk, by the way. Some systems crash when you do this. Other systems don't support it at all. So, you know, the goal is to model the behavior so we can see how well it works. And that's how we did it. So if you're really excited, you could do everything I just put on those slides at home. We used a program called RW Everything, which is this freeware. Well, it's actually shareware, but it's a program that you can use non-commercially for a little while to hack. And you can rewrite PCI configuration registers on Windows with it. It's really cool. So anyway, With no further ado, here's what we really did. Oh, yeah.
Hello.
I don't know why this is on.
Hello. So what Tom just talked about is basically the general concept. It could potentially be adopted on any protocol which supports RDMA, because you are using the underlying file system protocol to set up this whole thing, the mapping, and then from that point onwards you are just using RDMA directly to transfer data to memory. And I'm just going to talk about the SMB instantiation of whatever we call push mode, and SMB is just being used as a method of setting this up. So this is a quick review of what we have in SMB as of today. So SMB does almost like near zero configuration RDMA. So you just need to have RDMA capable adapters with the switches and stuff configured the right way. And we discover interfaces, we do multi-channel, we'll set up as many connections as needed, and then we support all these. We are layered on top of SMB Direct, which is a documented protocol. It provides a kind of socket-like interface on top of RDMA without worrying about all the nuances of pre-registered buffers and all that kind of stuff which RDMA requires. And we use two modes. One is the RDMA send receive for small messages, and then RDMA reads and writes for direct placement writes. Now this is just a recap of SMB direct placement for reads and writes. So the essential thing to remember is the server never opens up its memory to the client, and for good reasons, because it can sometimes, unless you have a tightly controlled data center situation or a secure data center, it could be undesirable to open up server memory to access by clients. So most protocols, even NFS I believe does this, but so the client registers a piece of memory corresponding to a particular chunk of IO buffers, and then the server pulls or pushes data. That's what we do. And the MS-SMB2 protocol defines how you get a token, a memory registration token from RDMA. We pack this up into a descriptor which contains a token as well as like an offset and a length, and then a scatter gather list of these, and then we send it out to the server. The server will pull or push data from the client buffers into its memory and then write it down to disk. So the important thing to remember, even though the data transfer is actually offloaded via RDMA, you still incur the cost of the SMB2 message processing, as well as taking additional interrupts. So for example, if you take a read, or let's say a write, so the server will get interrupted when it receives the SMB2 write message, and then it writes, it reads data from the SMB client's buffer into its own buffers, and then when that completes, it takes a second interrupt, and so it's at least 2 interrupts per IO on the server side. So the interesting thing about push mode is if you can take the CPU out of the picture, you are essentially getting 0 interrupts on the server, and that's what we're trying to achieve, and that will hopefully bring down the latency and so on. So these are the prerequisites for enabling push mode. So the first, as Tom mentioned, is a DAX file system. So you need to have an NVDIMM, a persistent memory device, either an NVDIMM or like Apache Pass kind of device, PM device, and on top of it a DAX, direct access enabled file system, which can provide you a view of the file, a direct mapping to the file, byte addressable mapping. And then, of course, you can always extend it to access the entire device by like synthesizing a file describing an entire device if you want. If you want to do push mode to a whole device itself rather than a file inside a DAX file system, you could do that too. And then the second thing we need is the ability to get a lease. This is not a typical exclusive lease, but it's a lease which a file system gives us, which guarantees that these blocks won't be moved around. There is no like defrag or whatever happening underneath it. So, because once you lock these pages down, it better stay, it should not be repurposed for anything else. So you need to have that ability. And then you need to have something, a protocol which doesn't require any processing of data on the server after it's written to memory, because then it kind of defeats the whole purpose, because you want the data to land in the eventual destination. So if you have things like encryption or decryption, which you have to do, then it's you need software intervention. And when we did this, we found that okay, RDMA does not impose any limits on the size of registrations, but most NICs do, because at least all the existing RDMA implementations always registered buffers only on need, so per I/O. So they used to be like small chunks, maybe a meg or 2 megs or 8 megs or whatever. But now you require the ability to register potentially very large regions of contiguous physical memory. And at least from the experiments, we tried with 2 different cards, so they kind of vary from 2 gigs to 1 gig. That's the maximum size of a registration that you could do, at least the Windows drivers support. And then we needed to make a few changes. We will also need to make a few changes to all the API layers below us to allow SMB direct to describe to descriptors of very large size, and then even changes to the NDK, which is the RDMA API stack on Windows, to allow for larger registrations and so on. So at least for the purposes of this experiment, we limited the size of registrations to whatever the NIC driver supports. So it's 1 GB and 2 GB. I think we played around with 2 values. And there's a reversal of roles, as I mentioned before. It's typically the client who registers memory and gives the descriptors to the server. In this case, the direction is reversed, because the server registers the memory and the client is the one pushing data. So we had to make a few changes to SMB server, the SMB direct layers, and the protocol itself, so to allow that. And well, you need a way to guarantee durability of data and persistent memory. So Tom talked about the flush, which doesn't exist right now. But we did the trick which he described by substituting a flush, by disabling DDIO and substituting a flush with an RDMA read. And then I also tried what I call a software flush. That's the last thing on the slide there. So that's a way by which you could get it working on an existing system without tweaking bits in PCI registers or whatever. So basically, the client does an RDMA write, and then it sends a flush operation without any data out to the server. And that server basically will look at the region written, and then it will use CPU to actually flush the data out into NVDIMM by using the CPU instructions like CLFlush or CLWB or one of those PM persistent memory instructions. So let's look at the steps, what the client needs to do to set up access to this persistent memory region. So we could do this on SMB easily, because it's easily implemented as an FSCTL or IOCL, which you issue on an open file handle. Now, basically, if you look at it, it has 3 parameters. First is the access flag, whether you want the memory registrations to be readable or writable or both, and then an offset into a file and a length. So typically, we would map the entire file. So the offset would be 0, and the length would be the 1 GB region or a 2 GB gigabyte region, whatever you want to do. And then we use the features provided by the DAX file system to get you the physical extents for the file. So typically on a block device, when you query for the extents, you get like LBA ranges. So querying physical extents for the file basically gives you a physical address length, basically a scatter-gather list of physical address ranges where this file resides on the PM device, persistent memory device. Now, for the purposes of RDMA, these physical extents are sufficient to program the RDMA device to register memory, because all what you're giving to the RDMA adapter is basically a base bounds separated list of physical memory ranges. You give this to the device, and the device will give you back a registration token, which describes the region. Now, we'll kind of talk about it later. You might need to obtain a virtual address mapping for these pages too, because if you want to do a software flush, that can be done only using a VA address mapping. You can't flush physical addresses, so you have to assign a virtual address mapping to these regions so that you can do software flush. And there are different ways of doing it. The trivial way would be to map the whole file, mmap the whole file into some address space, and then you can issue flush on whatever regions you want. But it may or may not be desirable because you are exposing the entire contents of disk to memory, where it's readable. If there's like a vulnerability or whatever, people can change the data and stuff. So you got to think about that. Or you could do it per I/O too. Anyway, we'll talk about that. Now, the third step, once you get the physical extents for the file, you register it with the NIC. And then once you make the registration, you get back a registration handle, and then you query the RDMA token, the memory region token, a remote token for that region. And then we use that token plus the offset and length to build an RDMA descriptor. So I qualified it as a large RDMA descriptor because up to 4 gigs, the existing protocol definition for an RDMA descriptor will, because the length field in there is only 32 bits. So if you want to go beyond 4 GB, you need a kind of a large descriptor format. And then the server sends back the descriptor to the client. Now, the interesting thing is these descriptors can be used only on the same connection where they were, well, I should not say connection. We'll come to it, but typically they are valid only on the connection on which they were registered. So if I'm sending the FSCTL on connection 1, this registration is valid only on connection 1. So all the data transfer, or you have to do this multiple times on each connection or something of that sort to get parallel data transfer. Now, this is how a client would do a RDMA read. So you first find, so when client gets a read from the higher layer, so you find the connection. You first look whether the handle was direct mapped, and if so, you find the connection where the direct mapping was done. And then all you do is you issue an RDMA read with the source as the token which was returned by the server, and the destination as the client side, the application's buffer. And you give this off to the RDMA stack, and the RDMA stack will transfer the data into the client's buffer without any more protocol involvement. So the only thing that needs to be validated is the region inside where you're reading should fall within the registered region and so on. Otherwise, RDMA will just kill the connection. So there is no protocol involvement at all. There are no server-side CPU interrupts. And there is just one client-side interrupt which gets generated when the RDMA read completes, so that you can complete the read back to user mode or whoever the caller is. So essentially, we have gone down from at least 2 server interrupts to 0, and client side, it kind of remains the same. So previously, you would get an interrupt when you receive the SMB2 response from the server, and there is no protocol processing at all. And write is exactly the similar thing. Now, except that you issue the RDMA write, and then after that, you might have to issue a flush, depending on what kind of semantics the application might want. Maybe it's a case where an application does like a write, and then a flush. But assuming it wants to flush every write, you have to issue an RDMA flush operation after the write. Now, the important thing to note here is that you don't need to wait for the write to complete before issuing the flush, because RDMA, the channel guarantees ordering. So you could issue the write and the flush immediately, and the RDMA semantics will guarantee that the flush will happen after the write completes. And then, as Tom described, you could map this to an RDMA read, which is what we did in our experiments. We replaced the flush with a read of length 0. It doesn't, or I think 1 byte. 0 is not valid, but basically we do an RDMA read of 1 byte in that region. And
0 is valid, but it doesn't provide a PCI
right?
Real deep detail. It's not
Okay. Now, the alternative implementation, which we also tried, is doing a software flush instead of an RDMA read. This basically, it's the same steps as before, except that after you do the RDMA write, we create a fake SMB2 write. I defined a flag called write flag flush only. It's not documented or anything. It's just for me to play around with. And we just give the write command the offset and the length of the buffer. And there's no data payload in the write. Now, the SMB2 server will receive the request, and then it will have to use the VA mapping, which it set up earlier, to issue one of these instructions, like CLW. Depending on what your processor supports, you have to issue one of these PM flush instructions on all the cache lines in that region. So if you're doing a 1 meg write, you have to break it up into whatever 64-byte cache line sized CLWB instructions. You have to do it in a loop to flush out the entire range. And for this purpose, you need a VA mapping. And we tried two approaches. One is the easy one is to map the whole file and have VA ranges ready when this happens. The other option which we have on NT is there's a fast way of giving a bunch of physical pages and getting a quick system virtual address mapping for those ranges. And then we tried that too, and the cost of both were about the same. It was not, at least not noticeable in my testing. And this one, and in this case, now you have a single server-side interrupt generated for processing the flush, the software flush. Now, coming back to protecting this mapping. So you want to make sure that only the appropriate people have access to this mapping. So the way RDMA does this is using what I call protection domains. So you create a protection domain, and then for every other RDMA object you create, you associate it with the protection domain or the PD. So connections, memory registrations, all these are tied to a PD. Now, in our implementation, the PD, a new PD is created for every new connection, at least on the server side. That's what, and even on the client. So for every new connection, you get a new PD. And because of that, these registrations are typically valid only on that particular connection. You could take the other alternative approach of having one PD and having all connections assigned to the same PD. But then it's very much possible that some other client could come in and like write data into your mapping or whatever. But might be possible under certain scenarios, but we don't do it. And because of our connection affinity, at least in my experiment, we don't get multi-channel load balancing unless you make multiple registrations, because one registration is tied to a connection, so all I/O to that, all push mode I/O to that registration will have to be forced on that particular connection. Now, the other additional concerns that we have are there failure modes, and how do you handle that? Because in the push mode variant, there is no server CPU involved. So if you want to build fencing and other kind of error recovery strategies, you have to be a little careful. So we can mix SMB2 writes with push mode writes, but you need to make sure that you enforce the right ordering. So if there's a failure in the push mode write, you want to make sure that there is nothing in transit out on the network before you issue the SMB write. Otherwise, things could land in the wrong order, and you would have like write-write conflicts and things like that. So the way to achieve that is to, if we ever do an RDMA push mode write, and the client wants to, for whatever reason, retry that write over SMB because it lost a connection or whatever it is, right? It has to make sure that the registration is removed from the server, so that that will act like a fence, so that no in-transit push mode writes will land up in that region after the SMB fallback has kind of completed. So basically, once you deregister the region, the late arriving RDMA, this is kind of like a time sequence of operations. So if you see here, you set up access to the direct map, and then let's say you're issuing an RDMA write, and let's say that that RDMA write is stuck somewhere on the network, it's in transit, And for client, let's say it timed out or it got a disconnect or whatever it is, and then it replayed that write over SMB. Now, as you can see in the last line here, the PMEM line, the content of the data changes from the light blue to yellow when the SMB write replay comes in. Now, let's say that you do a second SMB write to the same region. Now, the data content changes to purple. Now, if you do not invalidate the memory region, that stale RDMA write from the initial one could end up overwriting the purple one with the yellow one at the end, and you have to prevent that from happening. And the only way, at least we could think of to prevent that, would be to deregister before you attempt retry of a write on a secondary channel or using the protocol or whatever it is. You have to make sure that all previous registration or I/O to that region has drained, and the way to do that is to kill the registration, to close down the registration, so any RDMA writes would fail there.
Isn't this only a problem if you have a shared protection domain? I mean, once the connection and the protection domain are gone, the memory regions are automatically invalidate, right?
The question is this a problem if there is a shared PD backing the memory? I don't think it's a problem with the shared PD, because you're tearing down that explicit. The client ensures that the particular region is toned down. Then if you get I/O to that region, the RDMA will kill the connection, as far as I know. Is that right? Or?
Well, I thought, I don't understand how a write can be replayed, an RDMA write can be replayed if the connection's gone.
No, there are two. Okay, so
The second replay is not an RDMA write. The second replay is a standard SMB write.
So what is it colliding with exactly?
it's colliding. So the question is, what is it colliding? I think I didn't probably describe the full scenario. Let's say that there are two connections to the server, and the registration is done on connection 1. Now, we issue the RDMA write, and for, let's say, after a second, the client timed out, and now it wants to replay the write via regular SMB on the second connection, connection 2.
The connection hasn't broken on the first connection. It's just
Right.
taking a long time to complete.
Or at least from the server perspective, the connection hasn't broken. It could have been broken on the client side, but there could be a disconnect between when the disconnect arrives on the client versus server. The RDMA write could be hanging around in the network for,
Bottom line, Chuck,
Yeah.
you get paid to be paranoid. It's an enterprise class server. So some of these are very unlikely, but nonetheless possible.
that's right. And we have the same kind of situation in SMB with multi-channel replay, where we can actually handle this in the protocol. But here there is no protocol involved for the RDMA write. So we have to kind of take the brute force approach of tearing down the mapping. Now let me go to what we measured after doing all this. And this is our first. We tried on this on 2 systems. The first system is an NVDIMM system. They are typically, I think, 16 gigs of NVDIMM, and we have a 25 gig RDMA adapter. I'm not quoting the adapter because these are just experimental numbers, and I don't want to quote any particular hardware or whatever. But now we have formatted the NVDIMM in DAX mode with NTFS with a single 2 GB file. And we do a single RDMA registration of the entire 2 gig range. And we have an internal tool called CFS test, which we use to generate I/O, and I kind of modified it to issue that FSCTL basically on the handle to map the file. Important, don't quote these numbers anywhere, but these are just experimental numbers. So let's see what we have here. So the first column out there is the queue depth and the I/O sizes, and the columns to the right, they basically, I'm trying to measure the latency of I/O. Okay? So the first column, the SMB3 column, is regular SMB direct placement using RDMA. So you would send an SMB to read request, and the server will RDMA write data into the client buffer and then complete the read request. So those take about 51 microseconds. For Q depth 1, Q depth 2 is about the same. I think about 4, till about Q depth 4, it stays there, and then it starts increasing. Now, with push mode, you can see here that it's quite a bit of improvement from what we have. So it's at least 3 times lower latency than a typical SMB2 RDMA write. And the added thing is there is no, you look at the server CPU utilization, it's just 0. There's nothing, no CPU at all involved on the server when it's operating in this mode. And you can see there's across the board for various Q depths, IO sizes, there's fairly significant gain. So when you come to higher Q depths and higher IO sizes, you are kind of bound by the bandwidth of the connection at that point. So you don't see more gains after that. But it's a pretty good win. And we here at least we have mapped 2 gig range the file, and then the block size is specified here, 4K and 64K. These are the variations. Now for write, same setup. SMB3, the regular path is about 81, 84 microseconds. Now, the first step we tried is push mode. So you do an RDMA write to persistent memory, followed by a software flush, which is a modified SMB2 write command with that flush-only flag, which I described earlier. So that's, even with a software flush, it's still significantly lower. It's only about 26 microseconds there. And the last column there is the trick which Tom described about twiddling those bits in the PCI registers and then doing a RDMA write followed by a 1-byte RDMA read. And since these are pipelined, it doesn't actually change the numbers at all. So if you go back to the previous slide, it was 15. Actually, it's better here. OK, that might be a measurement variation, I'm guessing. But there is no impact on doing the RDMA read because both these things are pipelined and there is no read doesn't return any data. You're just asking for 1 byte. So that's the first setup. Yes?
Noticing the last row, the DDIO disabled latency is higher than the software flush latency. Is that a consistent result for 64K, 32K, et cetera? And so would you consider maybe switching to using software flush in those cases?
OK, the question is, sure. Question is that the DDIO, the last row DDIO number seems to be higher than the software flush number. I did not do a very exhaustive. I think I tried 2 times, and I don't think I can draw a hard conclusion on whether they are accurate or not, but that would be surprising, but yeah. Yes. Now, the second setup is a more interesting setup, so to say, because these are based on the Intel 3D Crosspoint Optane DIMMs, the new ones, and they go to much larger sizes, like 700 gigabytes or something. I think that was the largest size I saw. And this particular one has 12, 128, 126 gigabytes. I have this funny sizing. And it's a different RDMA NIC from a different vendor. Same setup. But of course, we can't do these kind of large regions. And for this particular RDMA NIC, we could do only 1 gig registrations. It wouldn't support 2. Now, the interesting thing is this system turned out to be somewhat slower than the other one was 14 microseconds. This is 29. We were seeing double the time. And first, I kind of thought it was probably due to the Intel Crosspoint DIMM latencies. But I actually, what I tried was I memory mapped a file in regular DIMM, just regular memory, not even bothering with the Crosspoint DIMM. And I still got the same number. So it's probably not a PM problem, but more an RDMA driver or NIC issue because it's a different RDMA NIC. Anyway, the comparisons are still valid. They both SMB and both of them are slower, but the ratio between them are kind of about the same. And for write, the only noticeable, again, there is improvement here, but push mode and with DDIO disabled and push mode with software flush, they kind of turned out to be about the same. So, which again kind of leads to my observation that there is something which is impeding the latency of the RDMA reads and writes. The software doesn't seem to add much. So anyway, we need to study this, and the RDMA NIC guys are looking at it. And now let me just briefly talk about what could we use this for. So some thoughts. So this can be generally done only at the lower layers of the stack, because most of the time when you write data to a server, you would want it to be like three-way replicated and all that. So if you have processing on the server. But at the lowest layer of the stack, where maybe below the replication layer, you can use this because the data can be placed directly in memory. And like a persistent log replication, for example, where you have a node which wants to write persistent log entries to multiple nodes. So this can work because log is just a file. You map the log file and then just keep pushing data into the log. And we have S2D on Windows, which is basically disks exposed over SMB. So maybe those layers could actually map a whole PMEM device as a disk and then expose it to clients. And again, third example here is not persistent memory, so to say, but VM migration from node to node is a typical scenario where you have you have a cluster running VMs and you want to move the memory of one VM to another. This could be a very nice way of doing it, because all you need to do is create memory for the VM on the other node and just push the data across. It doesn't land in persistent memory, but in just regular memory. And then worth considering are the security issues, which we have to worry about when you open server memory to clients, and what kind of scenarios this is interest. But at least my take is that it's mostly data center, secure data center friendly, and then whether you can use shared protection domains and so on. So these are my thoughts, and that's all I have. So it's a good experiment, at least to kind of prove that there is a win here. It might get better, but at least these are the numbers which we have, and hopefully we'll see it in SMB2 or maybe somewhere else soon. All right, thank you guys.